All right, let's jump right into this explainer. Today, we're doing a total teardown of the ultimate engine powering modern artificial intelligence, gradient descent. You hear the term thrown around constantly, but today, we're actually popping the hood to see the moving parts. As your master mechanic for the day, let's just quickly flip through our diagnostic manual. We're going to cover the engine of modern AI, escaping the memory trap, navigating the lost landscape, translating theory into code, and finally, diagnosing system failures.
So, starting right off with Section 1, the engine of modern AI.
We absolutely have to start here, because, look, this isn't just some dusty academic theory. Without gradient descent, GPT-4, ResNet, autonomous driving, they literally would not exist. In machine learning, success is defined by a mathematical formula called a loss function, right? Our entire goal, the whole game, is to find the exact parameter configuration that makes that error number as close to zero as possible. If you can't find that mathematical minimum, your system is completely useless. It's really that simple. That's why this iterative optimization algorithm is non-negotiable. Every single weight and every neural net you'll ever build is updated using a direct descendant of this exact engine. Okay, moving on to Section 2, escaping the memory trap. Let's actually look at how this evolved from early historical failures to the engineering reality we deal with today. Because, it wasn't always obvious that gradient descent was the holy grail. Back in the 1950s, researchers like Haskell Curry were tackling nonlinear systems, and originally, they tried using Newton's method. Conceptually, Newton's method sounds incredible. It looks at the second-order curvature of a function to try and just leap straight to the mathematical minimum. Sounds ridiculously efficient, right? Well, they hit a massive computational brick wall. Let me be absolutely clear about why we do not use Newton's method in modern AI. To pull it off, you have to compute, store, and invert the Hessian matrix. So for a tiny, modest model with just 1 million parameters, that matrix has 1 trillion entries. 1 trillion. That is a massive n-squared memory bottleneck. Even with the craziest GPU clusters we have today, trying to invert a trillion-entry matrix every single training step is mathematically and computationally intractable. It is a dead end. So we simply don't do that here. Gradient descent trades that perfect mathematical jump for a computationally cheap, guaranteed downhill step. By relying exclusively on first-order information, just the local slope, the computational complexity drops to O of n. It scales linearly, and that right there is exactly why gradient descent won. It actually scales to the billion-parameter behemoths we run today.
All right, Section 3, navigating the lost landscape.
To understand how local slope navigation actually works in practice, we need 2 prerequisites. First up, gradients. You can't navigate without a compass, and in our engine, the gradient is that exact directional vector. Mathematically, it points toward the steepest ascent. But since we want to go down, we just take the negative of that gradient. Second prerequisite, loss functions. Just picture a rugged, massive mathematical mountain that maps every possible set of parameters to an error value. The absolute lowest valley on that mountain, that is our ultimate goal.
Now, I want you to imagine being blindfolded on this mountain. You can't see the valley at all. All you can do is feel the ground immediately beneath your boots. You feel the slope, iteratively compute your gradient vector to find the steepest path down. Take a strictly scaled step, stop, reevaluate, and do it all over again.
We can actually visualize this learning state like a hiker navigating down a topographical contour map. Think of the step size as a gradient vector arrow pointing down the slope. What's really cool here is that you can physically see the model learning. On steep slopes, that arrow pulses rapidly. The gradient magnitude is large, so the model is learning incredibly fast. But as our hiker gets closer to the flat minimum at the center, that pulsing slows right down to a crawl. The learning just naturally tapers off.
But here's the catch. This requires the perfect step size, which we call the learning rate. And if you've ever trained a model, you know the absolute pain of getting this wrong. If your learning rate is too high, your hiker violently bounces and ricochets aggressively off the canyon walls, totally frustrating the math and risking complete divergence. Too low, the hiker moves at this painful glacial crawl, and your model takes literally weeks to train. What you need are those optimal, smooth, perpendicular steps right across the contour lines. Which brings us to the master equation. Your new parameter position equals your old parameter position minus the learning rate scaled against the gradient. It's an incredibly elegant, simple equation that governs every single step down that mountain. Moving to Section 4, translating theory into code.
Okay, enough chalkboard theory. Let's validate that what we're talking about isn't just some abstract concept. You transition from that math equation directly into this engineering reality, optimizer.step in PyTorch. That single line of code is the literal translation of the math. When you call it, you are firing off a vectorized instruction across thousands of GPU CUDA cores, updating billions of parameters all at exactly the same time.
The crucial takeaway here is that gradient descent maps perfectly onto every piece of modern architecture. In a CNN, it's shifting 4D kernel tensors to find edges. In a transformer, it's updating the attention matrices to figure out what words matter. In diffusion models, it's nudging UNet parameters to strip away a noise. It is the universal language of model improvement.
Underneath the hood, we are literally just moving memory around. Your parameters and gradients are stored as contiguous 1D arrays of floats in GPU VRAM. The update itself is a highly parallel fused multiply-add operation. We're talking microseconds here. In fact, a 1 billion parameter model takes up 8 gigabytes of VRAM just to hold the weights and gradients for this one step. The descent update is almost never your bottleneck. Computing the gradient during the backwards pass is where all the actual heavy lifting happens.
All right, final section, number 5, diagnosing system failures. Look, even the best engines misfire. When you push billions of parameters through an algorithm, things are going to break. So let's open up the troubleshooting guide. If your loss suddenly hits NaN, it means your learning rate was so massive it shot your hiker completely off the mountain. You need to reduce it or clip your gradients immediately. Seeing zero progress? You're probably stuck on a saddle point where the gradient flatlines before you reach the bottom. And if you see violent zigzagging, your model is just oscillating wildly in a steep ravine.
To fix a lot of these headaches, especially the saddle point trap, engineers don't actually use full batch gradient descent. Instead, we rely on many-batch stochastic gradient descent. By computing just a subset of data, say 256 examples, we intentionally inject statistical noise into our compass. And that noise is a lifesaver. It acts as an implicit regulator, bouncing us right out of those unstable saddle points, keeping us from getting trapped in sharp minima, and ultimately forcing the model to generalize way better.
I want to leave you with one final mental model. Lock this into your brain. Imagine a massive billion-dimensional bowl filled with thick, viscous honey. Now, drop a heavy steel ball bearing right into it. That ball, those are your parameters. Gradient descent is simply the physical law of gravity governing its slide to the bottom. The slope dictates the gravitational pull. That's your gradient. And the honey's viscosity? That is your learning rate.
But that leaves us with a huge cliffhanger. What happens when the landscape isn't a nice, simple bowl, but a chaotic, billion-dimensional terrain completely filled with treacherous saddle points and endless flat plateaus? Pure gravity just isn't going to cut it. That structural chaos is exactly why engineers had to invent advanced optimizers like Momentum, Atom, and SAM. And that is exactly where our exploration of this engine is going to go next. Think about how you would alter the physics of that bowl to force the ball down faster. And we'll see you in the next explainer.